Sample exam 6, question 10. Let x1 through x16 be a random sample from a normal distribution with mean mu and variance 16, and testing the null hypothesis that the mean is 0 against the alternative hypothesis that the mean is 1. The critical region is x bar greater than k. If the significance level of the test is 0.03, then the respective values of k and the probability of a type 2 error for mu equal 1 are. Problem number 10. I have two possibilities for this problem. I think both are correct, but one matches the answer and the other is just very close. So here we're given the rejection region. So under the null hypothesis, the probability to reject would be alpha, which they give as 0.03. So here if we subtract the mean, which is 0 under the null, divided by the standard deviation associated with x bar, we get z is greater than k is equal to 0.03, which when you look this up in a table, I get k is equal to 1.89. Now to calculate power under the alternative hypothesis, again, subtract the mean, but we're under the alternative, so it's 1, not 0. Divided by the standard deviation, we get z is greater than 0.89, which when you look this up is 1867. Now the answer is closest to C, and the only way that I could come up with their solutions, and I don't know what tables are available on exam day, but if you use linear interpolation, you can come up with the answer that they have. So here in the normal distribution setting, so 1.96 and 1.64. So 1.64 corresponds to a 0.05 tail. 1.96 corresponds to a 0.025. So to find the 0.03 tail, if you use linear interpolation to find roughly what the distance between those two, where this would be 0.05, you come up with 1.9, which is what they provide as one of the answers. And then if you use 1.9 in your power calculations, you come up with the answer that they provide. And then linear interpolation is you let you have your 2 points and you go from t and 1 minus t, and this needs to be 0.01. You find that t is 0.05. So you go 1/5 the distance up this. So the total distance is that 196 minus 164. Taking 1/5 of that is 0.06. So you subtract 0.06 from here, 1.96, and you get 1.9. And then this is the only way that I could come up with their answer. Number 11, suppose a one-way analysis of variance is performed on 6 groups with 3 observations each in 4 of the groups and 2 observations each in the remaining 2 groups. If the value of the usual test statistic for testing the null hypothesis that all the means are equal is f equal to 5.01, then which of the following statements must be true? Number 11, we're in a ANOVA setting, and they provide the F statistic. There's 6 groups, so the numerator degrees of freedom is 5. Denominator degrees of freedom is n minus the number of groups, so it'd be 10. So F of 0.05, 5 and 10 degrees of numerator, denominator degrees of freedom is 3.33. The test statistic is bigger than this, so we reject the null hypothesis. Answer is A. Number 12, let x have the density function f of x given there, where alpha is greater than 0 and beta is greater than 0. If beta is equal to 6 and alpha is equal to 5, what is the mean of 1 minus x raised to the negative fourth power. Number 12, we want to find the expected value of 1 minus x raised to the minus fourth. So you put that in, integrate over all possible x from 0 to 1. This is the density they provide. Now we combine this piece with this piece. So it reduces it to 2 minus 1. But whenever you're doing expectation, I think the goal, or one of the goals I try to do, is to trick it and make it look like another density again. Okay? So this next step, let me explain. So the x comes down, that combines with this, you get this. Now to make this piece of density, we have to go gamma of 5 and 2, which is 7, and then gamma 5, gamma 2. So this integrates to 1, so it drops out. But if we're gonna bring this in the equation, then we have to take the opposite. So this piece times this piece is 1, and multiplying by 1 doesn't change anything. So you have to take the reciprocal of it, and then this piece comes down. Well, you're left with this, because this integrates to 1. Gamma's 5's cancel. Now gamma of 11 is 10 factorial. Gamma 2 is 1. This would be gamma 6, and this is gamma 7. That reduces to 42 for your answer. Number 13, a box is to be constructed so that the height is equal to 10 inches and the base is x inches by x inches. If x is a uniform distribution over the interval 2 to 8, then what is the expected volume of the box in cubic inches? Now, number 13, we're looking at a box and we want to find the expected volume of this box. So they give us that x is uniform 2 to 8. Volume is 10 times x times x. The density is f of x 1/6. So this expected volume, plug it in. You put this in the density. So 10x squared, which is this, divided by 6. That comes from here. Integrate x. You get 280 as your answer. Number 14, in a bivariate distribution, the regression of the variable y on the variable x is 1500 plus b times x minus 68 for some constant b. If the correlation coefficient is 0.81 and if the standard deviation of y and x are 220 and 2.5 respectively, then what is the expected value of y to the nearest unit when x is equal to 70? Number 14, we're given that y given x is distributed somehow with a mean, mu, and a variance. But the equation is linear in x. So y given x is linear in x. It can be shown, and if I remember, I'll put a link in this video how to show that if it ends up being linear, that the mean has to be this and the variance has to be this. So those go up here. And so the mean of y given x, or y regressed on x, is this. So you just plug in values, and we're given it's 1500 and 0.8, 220. Anyway, so it reduces to 1643. Number 15, let T1 and T2 be estimators of the population parameter theta based upon the same random sample. If Ti is distributed normally with mean, mu, and variance sigma I squared greater than 0, and if T is equal to B times T1 plus 1 minus B times T2, then T is an unbiased estimator of theta whose variance is minimized choosing B as so number 15, we're given two estimators of the of our population mean, and each are distributed normally with the same mean but different variances, and they provide the variances. No, they don't. Okay, so let's look. Here is our new estimate T, which is this, and we find the variance of T. Well, you take it into each of those. So but you have to factor out a squared. So that's B squared times the variance of T1, which is sigma 1 squared, and then it's 1 minus B squared, sigma 2 squared. And then it's 2 times the covariance of each of those, but the numbers also have to be pulled out front, and you get this. So now we want to minimize this, so we take the derivative associated with B. So here you get 2B sigma 1 squared. Here you get this. Now what I did here is multiplied this in to both of those and then multiplied that in, and you get so it's 2B times the covariance, so the derivative would be this, and then the derivative of that second term you get 4B covariance of T1 and T2. We set it equal to 0 and solve for B, and then you end up with this piece here, which is one of the answers. But one note is that we need to make sure that it's a minimum. So we take the second derivative of this T, and it ends up being, so if we take here, then we get just 2 sigma 1 squared. Here we would just get 2 sigma 2 squared. There's no B, so it drops out, and we get minus 4 times the covariance of T squared. Well, a 2 can be factored out, and then what's left is the variance of, actually this would be T1 minus T2. And since the variance is always positive, and taking it times another positive, you get a positive number. That shows us that it is a minimum. Number 16. Let X denote a single observation from a distribution with density function f of x given theta, and for x between 0 and 1 and 0 elsewhere, while theta is greater than 0. What is the best critical region of significance level alpha for testing the null hypothesis that theta is equal to 0 against the alternative hypothesis that theta is equal to 1? Number 16. We want to find the K, the rejection region. So here's our null and alternative, and the critical region is defined to if values less than K, where we take our null distribution, our alternative, and then we just plug those in. And that means that we take our distribution and plug in 0 where the theta was, and plug in 1 where the theta was. Now this reduces to 3x over x plus 1, and that's less than K, so you can kind of solve this for x, and you get x is less than this number. And we're going to call this is just some constant. Let's call it K prime. So x less than K prime is the rejection region. Now we want that rejection region to be 0, so being less than K prime under the null distribution, which is 2x, you can kind of see that from here. We only get 2x. Integrated, limits of integration, we get K prime squared. So that implies K prime is equal to square root of alpha. but k prime was our constant. So x less than or equal to radical alpha, or the square root of alpha. Number 17, if the probability of x is 0.25 and the probability of y is equal to 0.8, then which of the following inequalities must be true? Now, 17, we're given the probability that x is 0.25 and the probability of y is 0.8. And 1 just is always true. The probability of x is always greater than or equal to x intersected with something else, because it can only get smaller. Now, number 2 is not always true, can be true. Here's an example. If we let a random variable w be a uniform on 0 to 1, we let x be from 0 to 0.25, so the probability of x is 0.25. Y is from 0.2 to 1, so the probability of y is 0.8, but the intersection is 0.2 to 0.25, and that probability is 0.05. So this is not true always. Now, number 3 is it's an interesting case. My initial reaction was that it's false, but it is true in this case. So if we set up a Venn diagram and we set off y, so if we subset it and y is such that the probability is 0.8, now we want to subset off x, but notice for them, if they're mutually exclusive, there's only 0.2 left over, but the probability is 0.25, so x has to go some into the y region to be 0.25. Well, then that says if we want to look at the probability that x intersect y, that's equal to probability of x plus probability of y minus this. Okay, so if we take this to be as big as possible, then what we calculate here is less than. So 0.25, 0.8, and this is big as possible. So this is less than that. You know, if this is really 0.8 or 0.9, or then this is bigger than this. Well, this reduces to 0.05, which says that the intersection is always greater than or equal to 0.05. So it is true. (18) Let the joint density function of x and y be given by f of x is equal to kx y squared, where x is greater than 0, y is greater than x, and less than 1. What is the value of k? Now, number 18, we want to find the value of k that makes that a density. So we know that it's a density, that's what they tell us, and it has to integrate to 1. And the region is, if we integrate y first, it goes from x to 1, and then x goes from 0 to 1. And this is just standard integration. So integrate y first, you get y cubed over 3, limits of integration, plug them in. Integrate with respect to x. Plug in our limits of integration, we get k over 10, and then that must equal 1, so that implies that k is equal to 10. Okay, hope you enjoyed the video. That's all I have for today, to keep it relatively short. Tune in for the next 8 questions on sample exam 6. Subscribe so you don't miss it. Thanks. Bye.